This is Mr. Smith here, Algebra 2. We are still in section 7.4 part 2, and we are talking about logarithms. So as just a quick recap for my students present here. A logarithm is a new type of notation, and it allows us to talk about the inverse of an exponential function. So if I have an exponential function, I can talk about its inverse in the form of a logarithmic function. Okay. Logarithm is just a number. Nothing to be freaked out about. And I've found that it's helpful to students to think about this inverse relationship. Right? The inverse relationship is very useful. So for instance, if I have y equals 2 to the x power, and there's a logarithmic function that is log base 2 of x, that will be its inverse, and they'll undo each other. Right? So I know, you guys know how y equals 2 to the x works. And now this logarithm piece, it just undoes that. So everything the one function does, the logarithm undoes. Okay, that'll help. Now yesterday I tried to explain how this was working. I have a better approach to explain it, so I'm going to start with that. But it is imperative that you memorize those two ideas. And what you're really memorizing is the fact that a logarithm and an exponent are inverses. That's really what this says. But I want to verify to you that this is true, and I think it's a useful exercise. So we'll say log base b of b to the x, and let's assume for a moment that it equals some value z, and I don't know what that is. Okay. I want to show to you, I want to prove to you that z has to be x. Okay, that's my goal here. And the way I'm going to do it is I'm going to convert this into an exponent form. So remember, this is my base. This is the exponent out here, so b to the zth power, and this is what it should equal, has to equal b to the x. Okay, so all I've done is I've converted from the logarithmic form into the exponential form, and now we see that I get b to the zth power equals b to the x power. So what do I know z has to be? Right? By this presentation, the only way these two things would ever be equal is if z equals x, which means this thing right here doesn't need a z, it can be an x. Okay? All right, so you don't have to be able to replicate this. I don't expect you to be able to replicate it. I just want you to know and believe that this thing is really true. Okay? And by the way, these numbers have to match up. So this can't be log of 3. You know, these values have to be the same value. So log base b of b to the x. All right, let me show it over here. Same idea. I have b, and the exponent of b is log base b of x, and they say that that equals x, but for our purposes, again, let's assume it equals some other value, z, and I don't know what z is. Okay. And now I'm going to take this exponent form, and I'm going to write this in a logarithmic form. Okay. So log base b of z, this is what it equals, so of z. And now the exponent goes out here, so this is the exponent. This is log base b of x. So again, my goal is to determine what does z have to be, and to be able to make these things equal, z has to equal x. So again, this thing can be erased, and I now know that this has to be equal to x. Do you have to be able to replicate these two verifications? No, I don't expect you to do that. I just need you to know that this actually is true, it works, and I need you to have these two pieces up here memorized. And the reason that's the case is because we're going to look at some problems here that make use of those properties. Okay. So in example A, I have 10, and now I'm going to raise 10 to a power. Raise it to a power, and the power is the common log. So remember, this is log base 10 of 6.7. Well, taking 10 and raising it to a power, and then taking the log of base 10, those two are opposite operations. They're inverse operations of each other, and so this just leaves us with 6.7. Okay, let me explain that again. I have 10. I'm raising it to a power. The power is the log base 10. Those two pieces are opposite inverse operations of each other. They cancel out, and it just leaves me with the 6.7. a student asked in a previous class, they said, Smith, what if this was a 9 here? What if I had 9 to the log base 10? Those will not cancel out. Okay, the numbers have to match. This is a 10 here. This is a 10 here. The numbers must match for these to be able to cancel out. So if you look at the next part, you look at part B, the first thing you should see is, well, wait a second, Smith, the numbers don't match. So we need to make them match. And if we can't make them match, then there's nothing we can do, and I promise I won't give you that problem yet. We're not to that level. All right, but in this problem, I can make this match, right? So I'm taking log base 2 of 16. Well, these don't cancel out unless I can make a 2 here. And we know that we can by writing this as log base 2. And then this would be 16 as 2 to the 4th power. And this all to the x. And so if we think about this slightly differently, this would be log base 2 of 2 to the 4x power. Okay. All right. So when I take log base 2, and then I take 2 to some power, those pieces are now inverses of each other. Log base 2 and 2 to a power, those are inverses. They cancel out in the same way that if I square something and I square root it, those things cancel out. If I log base 2 of something and I take 2 to a power, those cancel out, and it just leaves me with the exponent, which in this case is 4x. Okay. Let me do this for 2 more problems to get you comfortable with this. Okay. So again, these look very similar. Again, the numbers have to match. So this is 10 to the power, and the power is log base 10. Remember, there's a base 10 there. If it's base 10, we don't write it. Okay. Of 4. So this is just going to equal 4. Because when I raise something 10 to the power, and I take log base 10, those are inverses. They cancel out. Okay. And part B, I'm going to rewrite this because the numbers don't match. So we rewrite this as log base 5 of 5 squared, all to the x, or 5 to the 2x power. And now I see I have log base 5, and I also have 5 to a power. Log base 5 and 5 to a power. Those are inverses of each other, and they cancel out, leaving us just 2x. Okay. At this point, you should be able to do the homework problems. If you're watching the video, the homework problems 28, 29, 30, and 33. For those of you who are in my class, I want you to go back through those problems and look at them now and see if they look a little bit better. Start. All right, so for our next problems, we're going to be working on finding the inverse of a function. The first step anytime we do this is we switch x and y. So x equals 6 to the y. And now we don't really have a way to solve this. The only thing at our disposal is to change the format from exponent form to logarithm form. So let's do that. So I get log base 6 of x equals y. So all I did, step 1, I switched x and y. Step 2, I wrote from exponent form to logarithm form, and this is the inverse. This is the inverse. Let me prove that to you graphically, or at least help you to see it graphically. So the red graph here is y equals 6 to the x. The green graph is y equals log base 6 of x. Y equals log base 6 of x. And you can see that there's a symmetry along this line here, y equals x. Okay. So these two are truly inverses of each other. Y equals log base 6 of x, and y equals 6 to the x. All right. In part B, I switch x and y. So x equals ln of y plus 3. What does ln mean? ln, the natural logarithm, it means that it's log So x equals log base e of y plus 3. And for these first couple days as we're experimenting and experiencing logarithms, you can write log base e, but eventually it'll just be so natural, so comfortable, you won't do that. Okay. So what I'm going to do here is I'm going to convert this into exponent form, right? It's in logarithm form. We're going to convert it into exponential form. So here we go. So this is the base, e. This is the exponent, x. And this is what it equals. E to the x equals y plus 3. I subtract out the 3, and y equals e to the x minus 3. And if you graph these two pieces, this piece and this piece, you will see that they are truly inverses of each other. Okay? And any graphing calculator will do that. Okay. All right. Okay. So why don't those of you who are watching at home, those of you in the class, try problems 7 and 8. Okay. I'd like you to try questions 7 and 8. We're finding the inverse. Okay, so step 1, you're going to switch x and y. Step 2, you're going to switch the forms. So in 7, it's in exponential form. You're going to put it in logarithmic form. In 8, it's in logarithmic form. You're going to put it in exponential form. All right. So why don't you work on that at home? You may pause the video now. All right. So I went ahead and switched x and y. And now we're going to switch our formats. So this will be log base 7 of x equals 2y. All right, this is the base. This is the this is what it equals. This is the exponent. Okay, this is the base. This is the exponent. This is what it equals. And I almost have it to say y equals. I'm almost done. The only thing is there's a 2 in front, and I want to know what y equals. I don't want to know what 2y equals. So we just divide everything by 2 or multiply by 1/2. So y equals 1/2 log base 7 of x. So this and this are inverses of each other. Likewise, if I come over to 8, I switched x and y. Remember that ln simply means log base e of y plus 6. So if I want to change the forms, this is going to be e to the x equals y plus 6. Again, we want to get y by itself. So we'll just subtract the 6. So y equals e to the x minus 6. Okay? So the only other thing we're going to talk about in this section is graphing. Okay? Graphing is just trying to help you get an understanding of what's going on here. Okay? So here you can see we have a graph y equals b to the x. That's this guy here, right? Y equals b to the x. And now here we have y equals the log base b of x. And they are inverses of each other. All right? So at the beginning part of the chapter, we worked on graphing these things. Well, now we're going to work on graphing logarithms. Okay. So let's talk about this for a moment. If I have y equals b to the x, the domain is from negative infinity to infinity. And the range is from 0 to infinity. Okay? We've seen this before. We saw this at the beginning of the chapter. We now want to talk about the domain and range of its inverse. Okay? The domain and range of the logarithm function. So here I'm talking about the logarithm function, and let's change colors to represent that. And so if we want to talk about the domain here, well, look at this graph. The red graph does not come over into this area. The domain is just going to be from 0 to infinity. But the range is going to be all real numbers now. Okay, the y values here are any y value. I can get out any y value. So what you should see, here the domain was negative infinity to infinity. Here that becomes what the range is. Here the range was 0 to infinity, and now the domain of the inverse function is 0 to infinity. So they flip-flopped. And that will always be true of inverse functions. The domain and range of any inverse function will be flip-flopped. Okay. By the way, this red graph, our logarithm graph, when we look at this and graph it, it gets closer and closer to the y-axis, but it never touches the y-axis. What do we call that? That's right, there's an asymptote. Right, the y-axis here serves as our asymptote for our logarithm function. Okay. Now, this is if our logarithm value is greater than 1, if the b value is greater than 1. If the b value is between 0 and 1, if the b value is between 0 and 1, we'll get a graph, again, that looks like this. Okay. And unfortunately, for any of my 8384 users, at this point, you can't graph these on your graphing calculator. Okay. For 8384 users, you don't have the ability to graph these yet. Okay. The Inspire users can type it in, and you can do it. There is a way, and eventually I'll show you the way, but that's not today. It's not in today's lecture. Okay. So here we go. I want to graph y equals log base 2 of x. Okay. And so I know roughly what it should look like. But if I want to know with more clarity, I'll make an xy table. Another thing that can be done is, remember, if this is y equals log base 2 of x, then its inverse function, and let me just come over here and do some scratch work, its inverse function is y equals 2 to the x, right? So whatever this function does, whatever y equals 2 to the x does, this one, y equals log base 2, has to undo it. That's what it means to be an inverse. So for instance, if I plug in an x value of 1 here, what value do I get out? Right, if I plug in 1 and I square, or I take 2 to the first power, 2 to the first power is just 2. Okay? So this function takes 1 to 2. It means that this function, the inverse function, must take 2 and go back to 1. That is the very definition of inverse. Right? Whatever this one does, if this one takes 1 to 2, then this one must take 2 back to 1. Okay? And now you can do these problems a little easier, right? Because we know pretty well how this is going to behave. Right? If I plug in an x value of 3, I get 8, which means when I plug in 8 over here, I've got to get 3. If you don't like that, let's try a different number. Let's say I have an x value of 1. What that means is log, the y value equals log base 2 of 1. Oh, what does log base 2 of 1 equal? And now is when your comfort with logarithms really is important. You need to understand or be comfortable with the idea, well, that means 2 to the y power equals 1, so y here must be 0. Okay. So to make the xy table is going to be a little bit difficult. But remember, you know how the inverse function, if you understand how this works really well. So maybe you rely on this knowledge to help you. Right? If this takes 3 to 8, then the inverse function must take 8, bring it back to 3. Okay. So when we graph this, we get 1, 0. That's this point here. I get 2, 1. Point here. That's not that point there. It's this point here. I get 8, 3. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. And so what we do is we get a graph that looks something like that. Okay. Likewise, if we were going to graph log of base 1/3 of x, we can make an xy table to do that. I also know that it's going to look pretty much like this guy, right? It's going to come down. It should go through the point 1, 0. It's going to be asymptotic along the y-axis. And so, let's see, here's 1, 0. Okay, so the graph will look roughly like that. If you want to be more specific, now you start picking some xy values, and you make that happen. Okay. Again, the domain in both of these cases, is from 0 to infinity, 0 to infinity. The range, all real numbers. And the second example, all real numbers. Okay. There's one last idea to see here about the topic of graphing, and that's our knowledge of transformations. It seems like you're never going to escape them. But the good news is, if you've learned how to do transformations back in Chapter 1, which is when I first introduced them, then all of these other problems about transformations you have gotten. Okay. I see a +2 here. What do you think that's going to do? Vertical shift. Up 2 units. I see a -1 here. X -1. That's going to give us a horizontal shift 1 unit to the right, or it goes the opposite direction. And of course, the question that we should start with really is what are we transforming? What was the parent function? The parent function was log base 3 of x. Okay, so that was the parent function. And whatever that looks like, which I'll put that roughly on here. Okay, so let's say that roughly is what the parent function looked like. Well, I transform it. How do I transform it? I take it up 2 units. Up 1, up 2. I take it 1 unit to the right, which on my graph, each line is 2 units, so I only went half of that. So 1 unit to the right. Now, when I moved it horizontally, I also moved this asymptote. All right, so now there's an asymptote right here. And of course, the graph is going to keep coming down. Okay. So, because I moved it horizontally, the domain is now going to be from 1 to infinity, and the range will still be all real numbers. One other thought here to help you understand the idea of domain. If I have a logarithm function, the x value always has to be greater than 0. Okay? A logarithm of 0 or less is undefined. So this value inside the parentheses here, that always has to be greater than 0. Okay? And so we have to pick our domains to do that. All right, so this concludes section 7.4, our introduction to logarithms. Thanks for your attention. Have a good day.